mention it yesterday. Let's mention it today. Make sure you get it. If I go back to this spring I was talking about yesterday, ideal spring, and here we'll attach a mass to it again. You don't really have to, but we will. And it's frictionless on the surface. And I pull it back to the right while I'm holding it back here with my hand. The spring is pulling it to the left. Okay, you got that? I'm holding it here. The spring's pulling it to the left. How much force is on the spring? Okay, imagine whatever number of newtons that is. What if we put a spring scale there and measured it? Okay, that's 20 newtons. I'm just making up a number. What if I then move my hand to right here? Would it still say 20 newtons? It would be less, wouldn't it? What if I pull it even farther than this? Would it say 20 newtons? It would be more, wouldn't it? So we did talk about the fact that the force of the spring scale varies. It's not the same everywhere. It depends on how far I pull the mass. That's what Hooke's law is about. You saw it, and you have all written down in your notes that you took for assignment A. You all wrote that equation down. F is the force of the spring. Okay, now, it's not the force of my hand. Although if I'm holding it there, they're equal. Here's the force of my hand, H. Here is the force of the spring. If I'm holding it at rest, they're in equilibrium, they're equal to each other. But this F is the force of the spring. Okay? If I let go of it, there's still a force of the spring, but that one went away because I let go of it. All right, so the force of the spring is what we're talking about in this equation. The X is is the displacement from equilibrium. That's equilibrium there. How far has it moved from equilibrium? That's X. Well, look, that's directly proportional. You would say from this equation, that is the equation, but force of the spring is directly proportional to X. Now, does that make sense? The farther I pull it to the right, the harder the spring is pulling back, right? If I increase X, that's even more newtons. Okay, so if I increase that, direct proportion. The K is the constant that makes it all work, which you learned when you read, is what? What's the K? It's a constant. It would say what constant? It has a name. You can call it the spring constant, which is what I usually call it, because it's really easy to remember. Sometimes it's also called the, I forgot what the other word is. The what?
Stiffness.
Well, it is about, that's what it's about, the stiffness. The spring constant is a number for the spring. It's a constant. Unless you replace the spring with a different one, it's the same. It's a number for that spring, but it has to do with the stiffness.
Wait, so
if it's a stiffer spring, then it's pulling back harder than if it's a really light spring, an easy spring. Some springs you pull, they're just easy to pull. Some are hard. Well, that's the K. The ones that are really hard, that's a big number for K. The ones that are easy, wow, that's a little number for K. So it is about the stiffness, but it's called the spring constant. Okay. Why do you think the negative is there?
Because it's pointing the other way.
It's the opposite direction from X, right? If X is to the right, it's moved to the right, that's X. The force of the spring is to the left, isn't it? So that's why the negative is there, because the force is the opposite direction from X. If the displacement is to the left, I take this mass and move it to the left. X is to the left, but the force would be to the right, wouldn't it? It's pushing it. So the F and X will always be opposite directions. That's why the negative's there. The K is just a number for the spring. If you want to know K, you divide that by this. So here's a very simple and often used problem. Someone will attach a mass to a spring and hang it vertically. And then they'll say, I want you to find K for that spring. Well, what would you do? You're going to use that equation to solve for K. So what do you do to get F and X? Because you need those two numbers to divide.
It'd be like,
How do you get F? Let's take them one at a time. K is going to be F divided by X. The negative doesn't matter. Now I'm just dividing these numbers to get K. So how would I get the force of the spring?
mg,
This is at rest.
mg.
Yeah, I heard you all saying it. Free body diagram on the mass. That's mg for the mass. That's the force of the spring. If it's not moving, they're equal. So you just, well, what is mg? That's the force of the spring. In this situation, it is. Okay, how do I get x then?
Just measure.
I measure. I look at the spring before I attach the mass, and before I attach it, it's just right there. And then I measure from there down to here. That's x. Just measure. How far, when I attach the mass to it, how far did it move? That's x. And that's the force that made it move, see? So F, x. Just divide those numbers and you get K for the spring. Does that make sense? Okay. At some point you'll have a lab with a spring, I hope. We'll get to all these labs. And if you need to find K, that's an easy way to do it. Now the best thing to do though would be to attach a whole bunch of different weights and make a graph. If you want the slope of your graph to be K, what are you going to put on the y-axis and what are you going to put on the x-axis? This is the force of the spring and this is what? That's how far it moved. So just keep attaching different weights because every time you attach a heavier weight, it's more force of the spring and these are equal. And then when you add a heavier weight, there's more force, it's going to go down farther. And so x is more. So here's a small f and a small x and then so on. You get these points and then the slope of the line would be K. That would be, experimentally, that would be a really good way to find K as opposed to just one piece of data. A bunch of pieces of data are represented in a graph. That's why we use graphs in labs because that one best fit line represents a whole lot of data. Whereas if I just measure it once, that's one piece of data. You hate to bang everything on one piece of data. Okay. Did I ever turn this on? I did not. Good grief. Is it on? Oh, it is on. Okay. Did you turn it on, Tony? Hey. There's Tony. He's the one that turned it on. I'm sorry this is going to YouTube and now everybody in the world's going to see your face. But his name may or may not be Tony. Okay. Yeah. You have to be careful nowadays putting your name out there. His name is really Biff. What's his name?
That's an interesting one.
You don't like the name Biff?
How did you come up with Biff?
What?
How did you come up with Biff?
That's his name.
Yeah, thanks. Thanks, Claire. That's this guy's name right over here. Because I don't want to have to edit out his picture, and so I'm going to give him a fake name.
You just admitted
Not that that's a fake name. All right, that was Hooke's law. Now, here's some more things to talk about before we get to the reference circle. Here's back to our same thing. There's a mass, frictionless surface, equilibrium. The spring is neither stretched nor compressed right now. All right, if I pull it over to here and then let go of it, we talked about yesterday, the fact that it would go back and forth like this. And we call that simple harmonic motion. You learned that yesterday. This distance from here to here, which we could call x in our equation, f equals negative kx. But if that's the farthest I pull it and then let go of it, it's never going to get farther to the right than that, is it? I mean, it's not going to come back here and then go farther over to the right. Can't do that. Conservation of energy. So it's that's the farthest it's ever going to be, and that is the definition for the word amplitude. the word amplitude means the maximum displacement. Okay, and the symbol for amplitude is a capital A. All right, so this is mostly just a terminology thing, but you need to realize that if the question is, hey, what's the maximum force of the spring? You just need to know the spring constant and the amplitude. Because the maximum force will be when it's maximum displacement. And so that would be A, the maximum displacement, the farthest you ever pull it. It should be the same back this way as well. If it's an ideal spring, it would compress the same distance. So that's the distance A, and this is also distance A from equilibrium. Okay, that's just getting the word amplitude in there for you. Another term we need to talk about is, and this term will come up it already has come up in circular motion. What's the capital T stand for in circular motion? That's the period, isn't it? The time it takes to go around once. Well, something moving in simple harmonic motion has a period also. What do you think it means? The time for what?
It takes
One complete back and forth. One oscillation. It's still called the period. Now it's not moving in a circle, so you don't say the time to go around once or time for one revolution. You say the time for one oscillation. Oscillation. I don't know if I spelled that right or not. And by definition, an oscillation is back and forth, one round trip. Just like the circular motion, it's when it gets back to where it started. Here it's when it gets back to where it started. How much time did that take? That's the period of oscillation for the block. Yes, Kyle.
So is amplitude only like from the center to one extreme?
Yes. Amplitude is measured from the equilibrium point, which is the center.
So
Yes.
is one oscillation from equilibrium to maximum to equilibrium, or is it to
No, it's from
maximum to minimum?
maximum back to where it started from. So it's all the way to the left and then back to the right.
But did it start from equilibrium?
Well, no, it did, but you pull it, and the simple harmonic motion doesn't start until you let go of it over here. Because the time it took you to pull it, we don't know what that is. Maybe you pulled it real slow. But when you let go over here, it begins. So the time to go all the way over and back is one oscillation, and the time for that's the period. Okay. Another thing you can measure with simple harmonic motion is the frequency. Have we talked about frequency for anything in this class?
Yeah.
We did. I know we did in chemistry, but have we in this class?
Yeah.
It is hertz.
And how much?
Frequency in this case, I bet we talked about it with circular motion, did we? With the time, the number of rotations per second. Anyway, that's what it is. Here it's the number of oscillations per second. It's the number of back and forth. I'll put OSC for oscillations per unit time. So it's how many, in 1 second, how many times did it go back and forth? That's the frequency. And that would be, oscillations per second would be measured in hertz, H-E-R-T-Z, or the symbol for that's capital H-Z. 1 hertz would be 1 oscillation per second. So if we really took exactly 1 second to go all the way here and back, then that's 1 hertz. The frequency is 1 hertz. Okay. So yeah, we did talk about this with angular things. The relationship between these two things, is there a relationship between T and F?
probably.
Yes. They are the what of each other?
And
They're just the inverse of each other. So make sure you know that T is equal to 1 over F. You can write it either way. If you know one of these, it's easy to get the other one. Just invert the number. If the period really was 1 second, what would be the frequency? It'd be 1. Yeah, it'd be 1 oscillation per second. Yeah. But that's because when you invert 1 over 1, you get 1 over 1. Okay. What if the period was 2 seconds? Takes 2 whole seconds to go all the way here and back. What would the frequency be? 1/2. It's the inverse. If that's 2, that's 1/2. Half of an oscillation per second. That should make sense. Half of an oscillation is from there to here. That took 1 second, another second to go back. The whole time was 2 seconds. All right, so know that. You probably already did, but if you didn't, know that. Of course, know what the 2 letters stand for. Simple harmonic motion, again, is when it goes back and forth. I should say this one last thing about simple harmonic motion itself. Its definition basically is that's happening. Simple harmonic motion is happening when that's true. Now, something has to be going back and forth, it has to be oscillating. But if it is oscillating, it's technically only simple harmonic motion when that's true. That is, the force of the spring is oscillating because there's a spring there. The force of the spring is equal to negative kx. If that's true, then that's simple harmonic motion. Okay. It's possible to have a messed up spring where that's not true, then technically that's not simple harmonic motion. Okay. There are other things that could be vibrating and it may not be simple harmonic motion. That has to be true. All right. Let's move on. Your homework, by the way, is the blackboard has kind of been messed up, so don't look at it until I get in and revise it. But you've already done A. Check that today. B is due Monday, and E due Monday. What happened to C and D? Asked the inquisitive student. We're going to do C in class sometime, and D we might just skip. But no, let me say it this way. I may never check D. D is notes on the next section or 2. Probably I'm never actually going to assign that and give you a homework grade for it. But I encourage you to read those sections. You always you understand it better if you read the sections. You do. Some of you don't really read the sections very much. You just kind of go through and pick out things and write notes. And so you get the homework grade. But I'm telling you, read the sections and you'll get it better. You'll understand it better. You'll be happy because you'll say, oh, I get it. This makes sense. Why didn't Claxton teach it this way? See? So read the book. Read the doggone book. Read it. Read it.
Yeah,
Steve, read the book. Do you ever read the book? Thank you. Steve, read the book. All right. I'm just letting you know. The homework is B and E, which are 2 sets of problems due Monday. All right, moving on. The reference circle. All right, we just finished a unit on things moving in circles. So here's my this. We just did it. We finished a unit where things were doing something like this. At least sometimes they were. Well, that makes a big circle, doesn't it? Take the outer part of the ruler, and if you trace it, it made a big circle on the board, didn't it? There's a pivot point at the other end of the ruler. All right, so here is the circle the ruler just made. It's not too bad. It's off a little bit, of course. All right, just pretend that's a perfect circle. And here's the center point of the circle, which was one end of the ruler. All right, if you, what is that noise?
I bet it's the STEM class.
What do you think it is? STEM class is doing that? So it could be. All right, imagine instead of the ruler, this is a string with a weight attached. And it's going around like this. And now, I don't know if this will help or hurt, but I'm going to say, imagine there's a light shining, the great big light shining down on this thing. And so what I want you to think about is where's the shadow, because there's a light here. The light strikes the mass, and there's a shadow behind it. So we're going to come in here now and put a wall right here that the shadow can show up on. And this is only going to move in a half a circle. Okay? Right now the shadow is, you know what I should do is get a different color. Right now the shadow is right here. But the light's shining right down on it. It's on the red wall, there's a shadow there. Okay, here goes the block. It's moving up to here. What about when it's right there? Where's the shadow? It's right here. Okay, it keeps moving in a circle. What about when it's right there? The shadow's here. What about when it's right there? The shadow's right in the middle, isn't it? Are you following me?
Yeah.
You keep going. Here, the shadow is here. Over here, the shadows move to that spot. Here, the shadow's at the other side. What's the shadow doing?
It's oscillating.
Then, without answering that, I'm just getting you to think, what's the shadow doing? Then let's say it does keep going, but now there's a light shining this way. And so we're following the shadow again. As the block moves on around, where's the shadow here? Well, now it's there. Moves on around, now it's there. Moves on around, now it's there. Moves on around, it's there. Moves on around, it's there. Now, what did the shadow do? It did what? There's a term for what the shadow is doing. It's simple harmonic motion. It's just like if there was a spring with a weight attached on a frictionless surface. The shadow starts out here, and it starts out, look how steep that is. It starts out moving kind of slow. The shadow does. Now, the mass is moving at a constant speed in the circle. The mass is not changing speed, constant speed in a circle. But because of this angle, the shadow starts out moving kind of slowly, but then it's going to get faster and faster and faster, and here it's really going fast, but then it's going to slow down, and kind of stop just for an instant, and then it goes back. It's just like if there was an ideal spring there doing that. That's simple harmonic motion too. It moves just like the mass would with the spring. Okay. Why did you point that out? Asked the student. Well, here's why. From here to here is the amplitude. It's the maximum displacement. That's the radius of the circle, isn't it? That's the radius of the circle, but the radius is the amplitude. That's the same thing, radius. This is an angle theta right there. Now, I'm imagining my mass moved from here to there. So let's just talk about that little part of the circle. And in doing that, the shadow moved from here to here. So it just moved up to here, straight down. Okay. So the shadow moved that far, but this whole thing, the actual mass is up here, and there's an angle theta. And so what you know, if I want to ask you how far did the shadow move, which is x, the shadow moved from here to here, I'm going to call that x, displacement of the shadow. This thing right here is a right triangle. Let's see if that's really what I want to do. A, which is the hypotenuse, times the cosine of theta will give me this distance here. Okay, so that's going to be x, not that. How far did it move? The distance from equilibrium to here was the amplitude. Well, now the shadow is here, so x is the distance from here to there. X is always the distance from the equilibrium position, or the center, to where the shadow is. Okay, but back here in this thing, if it started there and we pulled it to here, then it moved that far, then x was this. Same thing. How far, that's amplitude, that's now x, it's less than amplitude. Okay, so that's going to be a here, x is a cosine theta. A is the hypotenuse, cosine, because it's adjacent to the angle I know, theta. Well, wow, theta is, here's what I know. I know that omega is the change in theta divided by time, isn't it? So theta could be thought of as omega t, couldn't it? So let's put a cosine omega t. It's the same thing. Are you still with me? All right. Omega no, let's take the time. If the mass goes all the way around, that's 2 pi radians. If it goes all the way around, and the time to go all the way around is this, so that would be the angular speed, 2 pi divided by the period. So I think I'd like to plug that in. I may be getting ahead of myself. Let me stop and think. If I plug that in for omega, let's do that before I stop and check. I get 2 pi over t times t. Yeah. Now, what's 1 over t equal to? F, right? I don't know if I'm still on the camera. Here you go. That means, here's 1 over t. I can put in f for that, so that's equal to a cosine. All right, now I've got 2 pi. Instead of 1 over t, I'm going to put f t. Now, this whole thing is really equal to theta. Theta, though, is not a very helpful quantity for simple harmonic motion because in reality, something's just going back and forth. There is no angle. You know, the angle comes from us relating it to a circle. So that's why we need something besides theta. This equation here is not very helpful. However, what we've just done is we've converted theta into something that we can use. 2 pi ft. F is the frequency in hertz. We just talked about how many oscillations per second. And the t is the actual, and that's not the capital T, this is little t here. That's the actual time it's been doing it. So what if you want to know where is, or what is the displacement from equilibrium after, I don't know, 10 seconds? It's been going back and forth for 10 seconds. You just plug in 10 seconds there. And you need to know the frequency, and you need to know the amplitude. But if you know all those things, you can calculate exactly where it is. Along this line, where is it? That would be the x would be the distance from equilibrium, like we showed you here. If x comes out negative, it's back here. See, this is position 0 there. So all these are positive x's, and all those back there are negative x's. And the math will work. There you go. In fact, this equation right here, I think, I'm going to check that now, is on the equation sheet of your HE Physics 1 equation sheet, and somewhere on here I probably have it. X equal a cosine 2 pi ft, yes. Now make sure you calculate the 2 pi ft all together and then take the cosine of that, and you need to be in radian mode for any of this to work, okay? When you take the cosine of something, if you're in degree mode, you're not going to get what you're looking for. So multiply 2 times pi times the number of hertz times the number of seconds. Get a number and take the cosine of all that. Times the amplitude. And you'll see exactly where is it along this sort of an x-axis where that's position 0. Now, do you kind of get where that equation comes from? You're not ever going to have to derive it if you memorize it or can look it up on your equation sheet because it is there. But you need to know how to use it. This x is what is the actual position of the block that's moving back and forth. Where is it? How far is it from equilibrium? When you just solve that for x, that's what you have. Okay. All right, now I'm gonna write on the board equations that would be helpful, I think, for you to know from what I just taught you. And one of the, wait, what else is on the equation sheet? Something else is on the equation sheet, hang on. It is something that oh, here it is. I just told you that this is, I'm going to write it again, x is a cosine 2 pi f t. Okay, that's on the equation sheet. The other thing on the equation sheet is this. Now look at it. T is equal to 2 pi over omega, and it's also equal to 1 over f. Okay, we already talked about the 1 over f thing, but look at this. What is 2 pi over omega? What is that? You learned that omega is 2 pi over t. In fact, we wrote that right there. See that? Because that's one complete revolution if it's moving in a circle, and that's the time to go in one circle. All right, so omega is equal then to 2 pi over t, therefore t would be equal to 2 pi over omega. So that comes from this. That's where it comes from if you wanted something to kind of hook that on. That comes from this. But that's also on your equation sheet. You'll see that and that. Those two equations are on your actual equation sheet you'll have when you take a test. Okay, so you need to kind of understand what they are. I would also remember, and from those you can get everything, but omega is equal to 2 pi f. And we got that. We kind of derived that over here, where in place of omega, we put 2 pi over t, which turned out to be the same as 2 pi f. Sometimes it's just helpful to remember this, and that's not on your equation sheet, but it really comes from up here. You can get it from this. All right, omega is 2 pi f. Now here's why that's important. You're all saying, well, we don't need omega in this chapter. That's angular velocity. It's not moving in a circle in this chapter. But this chapter has come along and redefined omega for you. Because omega is directly proportional to f, the only thing you need is 2 pi, which is constant. So if you double the f, you double the omega. See, they're directly proportional. Because that's true, someone has decided to name this omega for this chapter angular frequency. Now that's important because there'll be questions that say, what's the angular frequency of this block that's moving back and forth? Now the frequency is just oscillations per second, so don't get that mixed up. F is oscillations per second. It's the inverse of period. But if they ask for angular frequency, it's the f times 2 pi. All right, so you have to get good at looking at the question on your test. Some of you still need to get better at that. When you take a test, sometimes you end up with, like the test we just took. I know some people haven't taken it yet, but that doesn't matter. The test we just took, one of the questions was, what is the acceleration? And some of you ended up with g equals something. That's not what it didn't ask you what is the acceleration due to gravity. It said just what's the acceleration. A was the question. Some of you solved for alpha. No, it didn't ask for angular acceleration. It just asked for acceleration. Make sure you understand what the question is on your test. Very important that you reread. Did I really answer the question after you think you're done? Go back and find the question. Well, here, see, the words can be a big difference. Did it ask me for frequency? That's f, or angular frequency? That's omega. Two different things. Okay. Okay. So I would just kind of, know that term is omega. That's what I'm telling you now. But omega is 2 pi f. And you can get that from up here. But if you just remember it's 2 pi f, it'll be easier for you. Okay. So that's angular frequency, 2 pi f. And those are the equations I would know if I were you from this little talk. Glad we've had this talk. All right, we're gonna work a problem. How much time do we have in here, Sarah? Is it till 9:50? Is it till 9:50? All right, let's work a little problem just to show you that you can do this. Just to show you that you can do this. Because you can. All right. I have an ideal spring with a block attached to it, position 0, and I pull it back 0.5 meters. That's the amplitude, 0.5 meters. The block is released, and the block makes 4 OSCILLATIONS in 10 seconds. You're measuring this like in a lab. You're counting it. It went back. You're 10 seconds. I'm timing it. Ooh, it did 4 of those in 10 seconds. Okay, so you know that. Now the question is, where is the block? Where is the block in 4 seconds from the time it was released? Okay. Well, you might can just try to think about it and figure it out, and you can get a pretty good answer sometimes that way. But what I want you to do is use this. X equals A cosine 2 pi ft. And solve it for X. Now if I stop, can you do that?
Mm-hmm.
A is 0.5 cosine 2 times pi. Ooh, what's F?
2/5.
The T is 4. F is the only thing we really have to figure out. Then the rest is plugging in. What is the F? 4 oscillations in 10 seconds. The F is the number of oscillations divided by the per second, right? So the F, it looks like it's 0.4. Is that really true? Yeah, I think so. All right, does anybody have an answer?
0.4.
What'd you get? 0.4? Is it positive or negative? X should come out to be negative 0.4 meters. It's a distance, it's a displacement. What does that mean? What's the negative mean? That's equilibrium. Negative means it's going to be back here to the left. And 0.4 is how far it is from equilibrium. So it's going to be 4/10 of a meter in that direction. It'll be right there. Okay, the whole amplitude was 0.5, so that's almost back to its other amplitude, but not quite. It's the amplitude's right there, and it went 0.5. Now, see if that makes sense. So let's think about it for a second. If it really goes 4/10 of an oscillation every second, then, or let's do it this way, let's think about it this way. If it goes 4 oscillations in 10 seconds, 4 seconds is a little less than half of that, isn't it? Okay, so let's say, and then in 5 seconds, it would have gone 2. Right? In 5 seconds, it would have gone completely here and back and here and back in 5 seconds. Is that true? 4 in 10, so 2 in 5. Yeah. So in 4 seconds, which is what the question was, 4 seconds, then it would have gone, I just lost myself. 4 oscillations, or 2 oscillations. So in 4 seconds, yeah, I'm just trying to get us to visualize it. And it only got this far, it got all the way here and back. And then it got to here and back to here.
1.6.
So it looks like to me it's probably on its way back to the right, but all we know is it's right here. And with still 1 second to go, and it's going to, in that last second, it's going to get all the way back. But in 5 seconds, it would be all the way back. I'm just trying to get you to think about how it's moving left and right. Yes.
When you get negative or positive,
How do you?
like from the equation,
The math, it just comes out negative, doesn't it?
how, like,
Did it not come out negative when you did the math? Or did it?
do what?
Did it come out positive 0.4 in your calculator?
It came out negative.
Does anybody know the answer to my question?
It came out negative.
Came out negative is what I thought. So you get the negative, it just comes out mathematically, it'll come out negative. If you do the math.
No.
Make sure you're in radian mode.
Oh,
Degree.
If you're in degree mode, you're gonna get a wrong answer every time.
Mine's going to be positive,
Okay, but that's wrong.
but you never thought.
I don't know what the positive means in degrees. Yeah, I don't know. The whole reference circle thing, when we put theta in there, that's based on it being radians, because omega is radians per second. So you need to be in radian mode. If you're in degree mode, you get a wrong answer, but I don't know what you get. I can't tell you that. I don't know. But if you're in radian mode, is everybody getting a negative 0.4 when you solve it? Okay. And the negative tells you it's to the left of equilibrium. If it was positive, it would be to the right of equilibrium. It doesn't tell you which way it's moving at the time. Is it on its way still to the left or on its way still to the right? We don't know that from just doing the math, but what we know is it's right there. At that instant, at the end of 4 seconds, it's right there. Okay. You think you see how these equations work and what they're about? I was hoping to get a little farther than just this, and so you have enough to do your homework, I hope. You still may, in assignment E, come upon a few problems that we haven't gotten to yet here in this lecture. So just try them. Try to look them up and try them. But, so don't just leave them blank. Give it a shot. Look back into the chapter and try to see what to do. But most of these I think you can do, based on what I've taught you today. We just didn't get quite as far as I hoped. Okay, that's it. Bell's going to ring in 25 seconds. Hope you have a good weekend. Hope you stay safe and healthy. I hope you get plenty of sleep. I hope you go to church on Sunday. I hope you hug your mom at least once a day all weekend, if your mom is in this country. Sorry, if she's not. All right, see you Monday, folks. Next week is coming home week. It's going to be a little crazy.
Everyone dress up. We need some points.